Welcome back to Physics Fundamentals. In this video, I want to talk about acceleration. The idea of acceleration is something that you should be familiar with from everyday life. A car has a control lever, a pedal called the accelerator, which causes the car to go faster. Going faster is one sense of acceleration, but in the sense of physics, we're going to be a little bit more general than that. Going slower, using the brake pedal in your car, is also a form of acceleration. And even turning the wheel, changing the direction of motion, is a form of acceleration. But if you keep in mind that idea, acceleration means the speed changes. That's a good place to be going into this whole thing. Before we get into the mathematics of acceleration, I want to quickly review. We looked previously at the idea of position and displacement. Displacement is the change in position, the final position xf minus the initial position x naught. And then the velocity we gave as s over t, or just substituting back in, that's xf minus x naught over t. And that version of the formula is honestly never useful, except as an analogy. Because this version of the formula, we assume constant velocity. We assume that the speed of the object never changes while it's doing this. Or we assume that the average value of the speed is good enough for our purposes. Either way works out to be the same numerically. And I just said that velocity gives us the rate of change of position. We want to think of acceleration as the rate of change of velocity. So we're going to end up with a very similar looking formula. There is no simple variable for the change in velocity. We're going to have to write it out. It'll be Vf minus V naught. But we take that difference, we divide by time, and we get acceleration. Before we go much further, let's think about this dimensionally. Let's think about this in terms of the units. I know that Vf is measured in meters per second. I know that V naught is also measured in meters per second. Those are the units we used for velocity in the previous lesson. I know that time is measured in seconds. I should get my head out of the way so we can continue this. That's the button for getting my head out of the way. If I take something in meters per second and I subtract it from something else in meters per second, I will be left with something in meters per second. And then I'm dividing. It might make more sense to write that as meters per second divided by seconds. Well, dividing by something is the same thing as multiplying by the reciprocal, so it would be meters per second times 1 over second, which gives me the units of meters per second squared, or meters per square second. Those are kind of strange units. They're not ones that you encounter much in everyday life, but those are the units for acceleration. The other thing that I want to talk about before we move onward is that while this is a perfectly valid formula for acceleration, very often we find it useful to rearrange it a little bit. If I switch the left and right, multiply by t, and then add V naught, I get a different version. It's a relatively straightforward algebra to go from one to the other, so I don't think it's worth trying to memorize both, but you're welcome to if that makes you happy. But that gives us the usual suspects. Most of the time when we're using this formula, we're either going to be solving for A or solving for VF. Knowing which one we need and being able to identify it is half of the battle. A baseball is thrown upward at 15 meters per second. It then experiences a downward acceleration of 9.80 meters per second squared. How fast will the baseball be traveling after 2.50 seconds? All right, we're talking about throwing something, we're talking about kinematics, we're talking about acceleration, and the only formula we have that involves acceleration right now says that Vf is equal to V naught plus AT. So let's go ahead and write down all of those variables. A baseball is thrown upward at 15 meters per second. That sounds to me like the speed at the start. That's going to be our V naught, 15.0 meters per second. The acceleration is given to us as 9.80 meters per second squared, and the time is given to us as 2.50 seconds. We're asked, how fast will the baseball be traveling? That sounds like a final velocity to me, which thankfully is the only thing that's missing. But I forgot something when I went through that so quickly. The baseball is thrown upward. The acceleration is downward. Those are different directions. It's up and down instead of left and right, but the same idea still holds. Well, we have a choice to make. We can either define upward to be positive or downward to be positive. I think the normal convention is that upward is positive, but that's not always going to be useful. But as soon as we've made that decision, that means that A, which is downward, has to be a negative number. Now we have everything we need. We can plug all of this into the formula. If I multiply 9.80 times 2.50, I get 24.5. And if I multiply meters per square second times seconds, one of the factors of seconds is going to cancel out, leaving me with meters per second. Then I have like units. I can go ahead and subtract. 15 minus 24.5, my calculator tells me, is negative 9.5. I guess I only have that much significant figures. Right, subtraction, so we round based on precision. The place value, tenths place in this case. 9.5 meters per second. And it's negative, so the baseball is going downward. The baseball is moving downward at 9.5 meters per second. All right, so at this point, if we are dealing with a constant velocity and we care about position or displacement, we're in good shape. If we're dealing with a changing velocity and we care about acceleration, we're in good shape. We do need to have a way of combining these things together. Unfortunately, the mathematics behind how this works relies on calculus, which is a little bit beyond the scope of this course. But if you smash those equations together that we've been dealing with and you apply a sprinkle of calculus, you get two other formulas that round out the equations of kinematics. Specifically, S equals V naught t plus 1/2 at squared, and 2as equals vf squared minus v naught squared. Combine those with the earlier equations, and these four equations are the equations of kinematics. Let's label it down here. And if you pay close attention to these equations, you'll notice that each of these equations has four variables. Well, this last one has three, but it's that weird case. I find it's most useful to group these equations based on what's missing. That first equation, S equals V naught t plus 1/2 at squared, does not have Vf in it. 2as equals Vf minus V naught squared does not have t in it. V equals S over t, of course, has A equals 0, Vf equals V naught. Right, the velocity is constant and there is no acceleration. And then Vf equals V naught plus At is missing S. So there's your problem-solving strategy. When you recognize that you are dealing with a situation involving kinematics, generally speaking, the goal is going to be write down all 5 variables that we've talked about: V naught, Vf, S, A, and T. Fill in the things that you are known, fill in the things that you know, the things that you're given, and fill in the thing that you are being asked to solve for. There should be one thing that is not marked at all. Hopefully that one thing is Vf, T, or S. Or hopefully you have constant velocity acceleration is 0. Using that information, you determine which of these formulas to use. You write down the correct formula. You rearrange the formula to solve for the variable in question. You plug in your numbers. You punch them into your calculator. You have a solution. This problem has a couple of interesting things going for it. An aircraft with landing speed 295 kilometers per hour approaches an aircraft carrier with a 205-meter runway. Find the minimum deceleration to ensure a safe landing. we're talking about things moving. We're going to call it a deceleration, but it's just an acceleration that we know is going to be in the negative direction, opposing the velocity. Right, but I know I'm dealing with kinematics, so I write down the 5 variables that we commonly come across, and I start trying to fill things in. The aircraft is approaching with its landing speed of 295 kilometers per hour. The runway, the distance we have to move in, is 205 meters. The acceleration is unknown. That's the thing we're trying to solve for, is acceleration. Then we have 2 questions left: the final velocity and the time. One of those had better be known to us. And if you stop and think about it for a minute, one of them is known to us. We know that this aircraft is trying to land. And if an aircraft is landing, it's going to come to a stop. When it comes to a stop, it will be traveling at 0 in whatever units we'd like. How about meters per second? So the time in this case is completely irrelevant to us. We don't care about it. All right, that's the first important thing that I've established here. The second thing that I noticed is I've got non-standard units, kilometers per hour. Before I can do anything else, I had better get this into matching units. So I know that 295 kilometers per hour is the same thing as 295 kilometers over 1 hour. That's how we deal with unit rates. And I know that there are 1,000 meters in 1 kilometer. And if you know offhand that 1 hour is 3,600 seconds, that's great. If you don't know that offhand, you probably know that 1 hour is 60 minutes and 1 minute is 60 seconds. So you can do this in a 3-step conversion instead of a 2-step conversion. But I have carefully set this up in such a way that the kilometers are going to cancel out and the hours are going to cancel out, leaving me with units of meters per second, which is what I am accustomed to. So I take 295, I multiply times 1,000, I divide by 3,600, and I get, let's see, I have 3 significant digits. So my initial speed here is 81.9 meters per second. And I'll go ahead and fill that in over on the left-hand side so I have a better reference. Now that my units are all in matching style, I can go onward and look for the kinematics equation that does not have t in it. Specifically, it's the equation 2as equals vf squared minus v0 squared. I can plug in all of my values. 2 is just 2. Actually, I'm getting ahead of myself. My goal is to solve for a, so I'm going to go ahead and rearrange the formula now. Mathematically, there's technically nothing wrong with solving, plugging in the numbers first, but it's a good habit to get into. Right? In classrooms, you never see a scenario repeated because we want to explore everything as much as can in as little time as we have. But in real-world applications, that's not what happens. you're looking at a particular situation and you're going to analyze that same situation over and over again, all day, every day, for a week, a month, a year, an entire 30-year career. So being able to rearrange and get the formula done once so you can plug things in the future without having to worry about it is a serious time save. All right, so VF is 0. V naught is 81.9. 2 is 2, and S is 205. All right, 0 squared is 0. Meters per second squared is meters squared per second squared. 81.9 squared, round to 3 significant digits, is 6,710 meters squared per second squared. And then 2 times 205 is 410. That 2 is an exact value, so we don't worry about it. The 205 had 3 significant digits, so that 0 is significant, and the units there are going to be in meters. 0 minus whatever is just the negative of whatever. We said that this was going to be a negative acceleration, a deceleration, so we're not surprised by that. (6,710) divided by 410 and round to 3 significant digits, I get 16.4. And then my units, I have meters squared per second squared divided by meters. Dividing by meters is the same thing as multiplying by the reciprocal 1 over meters. One of the factors of meters is going to cancel out, and my units end up meters per second squared, which is exactly what I expected. And of course I have a negative, so that carries along. I think my negative got eaten by my equal sign there. But we need to have an acceleration of negative 16.4 meters per square second, or a deceleration of 16.4 meters per second. The two ways of saying the same thing. All right. One last topic before I wrap up on this video is the idea of gravity. We're familiar with gravity. Gravity is the force that holds us on the surface of Earth, give or take a couple of approximations. In kinematics, when you are near the sea level on the Earth's surface, and near sea level encompasses basically everything we can think of, from the deepest land valleys to the highest land mountains, acceleration of gravity is, roughly speaking, constant. And it is in fact exactly that acceleration that we used in the first example, 9.80 meters per square second. If you want to get more precision, that's where things change based on where you are. That's actually all the further I know. But there's a nice printout. Someone did a very careful study in the physics lab in the Science Innovation Center at Youngwood and figured out to, I think, 7 significant digits the acceleration of gravity in that room. But yeah, 9.80 meters per square second is the acceleration of gravity. Whenever you have something that's dealing with gravity, you know that that's the acceleration we're going to use. We often use the symbol little g to represent that. We'll play around more with that as we move forward. For right now, I just wanted to throw out that that is a thing. I think I've gone on far enough here, so we'll wrap up with that. Thanks as always for joining me. I'll see you next time.